welcome to the first video in Unit 6, where we're putting together a lot of what we've learned in Unit 3, 4, and 5 to understand a process that we'll call carbonyl reduction. So you could imagine that each of these words relates to different concepts that we've explored over the course of this term. Reduction probably relates to the concept of oxidation levels. We've seen this with things like alcohol oxidations, for instance, and we've mostly focused on carbon. In our carbonyl chemistry, we've discussed in Units 4 and 5, which were more about reactivity of carbonyls and their structures. So to remind you what we know about oxidation, we could look at an oxidation reaction of carbon in a very general sense. So I'm not including any real reagents just to denote that we're doing an oxidation of some kind. Or we could follow the carbon here of 2-propanol from the +1 level to the +2 level. That would be our oxidation. A carbonyl reduction probably is going to be essentially the exact reverse of this reaction because it looks like we actually have a carbonyl as a product. If we were to reduce the carbonyl, we would actually just go backwards. So we could write reductions of carbonyls would be starting with some kind of a carbonyl. In this case, it would be a ketone, but it doesn't have to be. It could be an ester or an amide, any kind of carbonyl you want. And I guess H2. And I don't know, maybe we're going to need some other reagents. We're going to denote reduction with a brackets H. And then we would end up with this product. So we would be making a new CH bond, this one here, as well as a new OH bond, this one here. This looks a little bit like a reaction you learned about in OChem 1 when you learned about alkene hydrogenation, where you're adding H2 across a pi bond. Here we'd be adding it across the CO double bond. And if we wanted to reduce this to practice, it could work, but it turns out that this is extremely slow as written, so we would need a catalyst. So slow, use the catalyst that you've learned about before. So things like palladium on carbon, so a little bit of palladium metal divided up into some charcoal, or platinum on carbon, so same concept, but rather than the palladium, you're using a different element. And this can work. The issue you have is that the hydrogenation of carbonyls requires high temperatures and high pressures, at least for most kinds of functional groups. And that actually poses a kind of a problem for us. On an industrial scale, that's fine, right? We can actually do this reaction where we go from the +2 level back down to the +1 level. There's our reduction. Using H2 in a catalyst, but these pressures are extremely dangerous under like normal lab environments in some cases, and they're not always convenient. So like if you actually bought like isopropanol from a grocery store, for instance, like it might be made in an industrial scale using this type of chemistry, but it's not the only way that we can do these kinds of reductions. One of the things that we notice is that we're doing a lot of work to introduce this bond, this new CH bond, and we're doing that at the carbonyl center. That's kind of why we're calling this a reduction, right? We're introducing this bond to an element that's actually less electronegative than carbon rather than more. We would then need to think about other kinds of reduction reactions, so other carbonyl reductions. That we didn't want to use H2 gas with, for instance, or these catalysts or these high pressures. We would want to think about other ways to introduce a hydrogen. But I know something about the reactivity of the carbonyl carbon that I'm trying to reduce. I know that this center here is electrophilic. And that means if I'm going to form a new bond to that center with a hydrogen, I'm going to need a nucleophilic source of hydrogen atoms. How to do this? Nucleophilic H's. So let's look at a couple of reagents that actually have nucleophilic H's, or at least H's that could be nucleophilic. So the simplest thing you could imagine doing if you're trying to consider a nucleophilic source of H is to just put a lone pair on the hydrogen. That should make it nucleophilic. We know that that's going to generate a highly unstable anion, which we call hydride. So hydrogen, IDE at the end, that denotes negative charge. So here's our hydride. We know that we can't just go to the chemistry store and get like H- though, so we're going to need something that has a countercation. Normally we would think about this as something like sodium hydride or potassium hydride, right? We've seen sodium hydride before used as a base. We talked about that in Unit 5. But in principle, you could imagine that this could be nucleophilic, and that would react with our carbonyl center to make our new CH bond. So this would be an addition reaction, like the first step of a snack, essentially. And we would have an O- here, but you could imagine like after we did this, maybe we could add some acid or something like that to protonate the oxygen. And that would overall, over those two different events, constitute a reduction where we would go from +2 in this particular instance to +1. The important part is that we're going down in oxidation level. That's the reduction part. But what's curious about this is that the reaction doesn't work. It's never worked. Organic chemists don't use sodium hydride as a reductant or a reducing agent because for some reason, and we don't know why, it actually doesn't do this chemistry. So NaH is not a reducing agent. Not a reducing agent. It is a base. So all we could ever do with sodium hydride is deprotonate things. We're never going to be able to use it as a nucleophile toward really any electrophiles, including carbonyls. That's unfortunate. It would have been nice if we could have done something this simple. We're going to have to consider other kinds of reagents that actually are not actually H-, but behave like H-. Instead of NaH, or Na, we actually use a compound called sodium borohydride, which has the structure here. But what I want to focus on isn't so much the sodium, that's just a spectator cation, but rather the borohydride anion, which you can see here, where there's a boron atom surrounded by 4 different hydrogens, all bonded to the boron. 4 bonds to boron means the boron is negatively charged formally, but it has no lone pairs. So this is an unusual kind of a structural situation where boron has got a full octet, no lone pairs, but it is negatively charged. And that's like kind of a confusing thing for us to think about. We would normally look at a structure like this and say, oh, the boron is nucleophilic, but it's not, because if boron was nucleophilic, it would form a 5th bond and go over the octet rule. So a couple of notes here. B is not nucleophilic, but it turns out that the hydrogens are on the outside of the BH4 anion. Those are nucleophilic. One way you can rationalize this is that boron is actually slightly less electronegative than hydrogen. So you could think about the boron species as essentially being an inductive donor of electron density to a hydrogen. That makes the hydrogen somewhat partially negatively charged and therefore nucleophilic. So I'll show that on like just one of our hydrogens. I'll just choose the one here on the left. In reality, each of these 4 hydrogens is carrying some partial negative charge. The fact that boron is formally negatively charged makes boron even more powerful as an inductive donor than you might expect purely on the basis of electronegativity differences. So here we've got electronegativity of boron is less than that of hydrogen, and B is formally negatively charged, which makes it a more powerful donor. It's basically trying to get electron density off of it, and it's going to shove it into these kinds of CH bonds, which in turn makes the hydrogens nucleophilic and electron-rich. So this actually does work. These borohydride reductions are very useful. Chemists use them quite frequently. But there's one wrinkle here. When we talked about reduction reactions, we talked about adding 2 hydrogen atoms, right? Or effectively H2. All I'm showing right now is the addition of 1 hydrogen atom. So this is not sufficient to treat a ketone or some other kind of carbonyl-containing compound with just NADH4. We also need to think about how we can have a source of a hydrogen that would go to our O- as it's developing, either in one step or in multiple steps. But the idea is we would have to attach a hydrogen to the oxygen. So our actual borohydride reductions look a little different. We could start with the same ketone, and we would still use NADH4. I'll just use the acronym here. But we typically run these reactions in protic solvents, things like water or methanol or ethanol or isopropanol. So I'll choose ethanol. That's a commonly used solvent. And I just want to focus on the hydrogen of the ethanol. So I'll color code it. And I know initially what's going to happen is I'll form this anion. And that's going to be the hydrogen that comes from the BH4 itself. But we don't isolate this compound. So I'm going to put it in brackets. It's like an intermediate, not isolated. And that ethanol can now serve as an acid. So its pKa is about 15. Not negative 15, about 15. And that means that we protonate the O- that forms. And that gives us our overall reduction product. So we're actually getting one hydrogen each from two different sources. We're getting our OH hydrogen from our protic solvent. And we're getting our CH, so this one here, from our BH4. The way that we actually know that this is true experimentally is that we can actually use things like isotopes and follow where they go. For instance, you could use an isotope of hydrogen in your solvent and find out that that isotope is only incorporated at the OH group in the product, or you could put those isotope labels in the borohydride and find they only end up in this position in the product. Right? So this is actually well established by experiment. That means that when you do a borohydride reduction, and this is critical, you cannot use just this reagent or just this reagent. They are both required. Normally, I don't ask you to write solvents when you actually write out reaction plans, for instance. For borohydride reductions, the solvent is non-innocent. It's a reactant, and that means it needs to go in the box, or if you're doing synthesis problems, you need to specify. I also want you to be clear that it's not required to use ethanol, just a protic solvent. So this could be MEOH or ETOH or water or other alcohols. Any of those things would work. Okay, so let's look at a couple more examples where we're actually doing these borohydride reductions, and then we'll work through the mechanism of borohydride reduction to close the video. So let's look at this top reaction where we have like an aromatic ring and then we have an aldehyde functional group, and we would react this with a mixture of methanol, so there's our protic solvent, and sodium borohydride or NaBH4. What we can predict would happen is that carbonyls will be reduced by one level. So we can find our carbonyl center. It's at the +2 level right now in an aldehyde. We know that the reaction will happen only at the carbonyl. So that means the rest of the structure is likely to stay the same. And then when I reduce this carbon, and I'm going to have to introduce two hydrogen atoms, one at the CH, one at the carbon of the carbonyl and one at the oxygen. And that means I'm going to have to reduce the number of bonds between the C and the N. So I'll end up with a primary alcohol. So the pattern here is an aldehyde gets converted to a primary alcohol. So to practice this pattern, we could look at this example here where we have, in this case, a ketone reacting with sodium borohydride and ethanol, so a different protic solvent. What I'd like for you to do is pause your video and predict the structure of the products for this reaction. So one of the things that we'll notice if we look at the structure is that there's actually a couple of different carbons that are at relatively high oxidation numbers. Our ketone is at the +2 level, and the carbon with the two chlorines is also at the +2 level. But it turns out that sodium borohydride is specific for reactions at carbonyl centers. It'll ignore these halogens, for instance. And that means that we know that there will be selectivity for reduction of the carbonyl carbon. Once I've identified that feature of the reaction, it's sufficient to draw the rest of the structure over again. That's not changing. That includes the two chlorines. And now I have to adjust the oxidation level of the carbon that's a part of the ketone. So I'll remove one of the CO bonds. That does not mean the oxygen is gone from the molecule, just that it's now single bonded to the carbon. And I'll introduce two hydrogens, one at the C of the carbonyl and one under the oxygen. So that will give me a secondary alcohol. So our pattern here is a ketone goes to a secondary alcohol. Again, I'd advise you try not to memorize every permutation here, and more like see the patterns associated with oxidation level change. It's one of the reasons why we've learned about oxidation levels. It'll make your life a lot easier. So what we can do now is try to rationalize why this is true, that we're actually selectively reducing carbonyl carbons in the presence of other kinds of functional groups by actually looking at the mechanism of sodium borohydride reduction. So we could do this with a simple reaction. We'll go back to acetone as a substrate just because it's a nice small structure. So we've got our mechanism. And what we know is that this actually is fairly predictable on the basis of what we already know about carbonyl chemistry from SLO or units 4 and 5. It turns out the borohydride is involved in the reaction before the solvent really does much. And we don't even need to worry about the sodium. We'll just talk about the borohydride anion. We know that this carbonyl center here is electrophilic. And we know that not the B, which is negatively charged, but the hydrogens are nucleophilic. I'm just going to pick one of them. You arbitrarily choose one, but just one. And electrons within the boron-hydrogen bond, those are the least stable electrons in the molecule. This is kind of weird. We don't see it that often, but you have seen it before when you did things like alkene protonations, you use the electrons from the pi bond, right? We're going to use the electrons from this sigma bond to actually form a new CH bond. But to do that, I'm going to have to break the CO pi bond. So this is an addition, the first step of a snack reaction. That gives us our intermediate, where we've got an oxygen that's negatively charged. I'm not going to talk about the fate of the boron. It's kind of complicated. We could work through it. You could understand it, but it's not really important. This stuff becomes waste after it delivers the first hydrogen, so I'm just going to leave that out for now. And then this step, our solvent gets involved. So let's just do this with ethanol. It could be a different alcohol, for instance. And we know that we could do acid-base chemistry to transfer a proton from the solvent to our intermediate. So here we've got acid-base or a proton transfer, and that will give us the alcohol in our product and the conjugate base of the solvent. So this is actually a good place to review some of what we learned in Unit 2 about acid-base chemistry, and specifically evaluating how favorable this proton transfer is. So if I look at my starting materials, this is the acid. It has a pKa of about 15. In our products, this is the acid, and it has a pKa, it's an alcohol. So it's also got a pKa of about 15. Which means that our KEQ should be about 1. So like about half of your O- will become protonated to form the product you actually want. But there's a wrinkle. Even though the KEQ is about 1 for this, remember that this is our solvent. So that means that we have like thousands or millions of molecules that look like this for every one that looks like this. And that means that we're using Le Chatelier's principle again to drive the acid-base reaction to the product that we intended to isolate. So our acid-base reaction step is driven to the products by Le Chatelier's principle. So we're overcoming something that's really not preferred in any meaningful way by just dumping a whole bunch of reactant in by virtue of using this protic material as solvent. The other way around this would have been to use something that's much more acidic, so a pKa that's like a lot less than 15, and then we wouldn't have to play this game anymore. The equilibrium constant would just favor going to the products, right? We'll see examples that look like that in the second video for this series, but when you're using sodium borohydride, really the protic solvent's sufficient. We don't ever have any issues with this equilibrium to speak of. The last aspect of sodium borohydride reductions that I want to discuss is the concept of chemoselectivity, which essentially means if there's more than one functional group in a reactant, whether one of those functional groups reacts in preference of the other. So for instance, we could look at a reaction which would involve a ketone and an ester and sodium borohydride along with a protic solvent. So the question, I guess, would be, which of these carbonyls will actually react? Or maybe they both do. Chemoselectivity would be a situation where only one of them actually reacted, regardless of how much excess reagent we have. So like, imagine we had 1,000 NADH4 molecules for every one that looks like this. There's more than enough nucleophilic H's to reduce both carbonyls, but maybe only one of them reacts. It might be hard to predict. We do know a couple of things about the system, though. The carbonyls have different electrophilicity. So we know that our ketone is more electrophilic than our ester carbonyl, because the ester carbonyl has this resonance donor group that's missing from the ketone. That tells me that the ketone should react with nucleophiles more quickly than the ester does. This would be the basis for many kinds of chemoselectivity, where one of your sites reacts more quickly than the other, but the difference has to be really large to actually get good selectivity. Open question, right? Well, let's do the experiment. So you actually mix all this stuff together and you isolate a single product. It looks like this. So it looks like our alcohol came from the ketone and our ester remained unchanged. So our ketone was reduced, but our ester doesn't react. What we find in this example, and you could verify this using other kinds of reactions that involve both esters and ketones, for instance, is that this is general. Sodium borohydride does not reduce esters. So I put this asterisk by doesn't because if you're a chemistry major thinking about doing a bunch of organic synthesis and research, for instance, this is not strictly true. We've actually developed some reaction conditions using special solvents and things where this does work, where NADH4 will reduce esters. For this class, though, we're going to treat this rule as true, that esters do not react, whereas ketones, for instance, will. So we actually find that sodium borohydride reductions, they're pretty chemoselective. We have learned that they are selective for ketones in the presence of esters. And in a previous section of the video, we even saw they were selective for things like ketones in the presence of alkyl chlorides, which is a kind of a nice feature that we can look at complex molecules, maybe things with even more functional groups than this, and we would have a fighting chance of being able to reduce one species, or one functional group, excuse me, over the other. Fundamentally, what this comes from is the fact that there are such big differences in electrophilicity between a ketone and the ester that the rate of reduction of an ester with sodium borohydride is minimal, almost zero, right? Whereas a ketone reacts pretty quickly. Generally, like an hour or two is sufficient for the reaction to be done. So if this gap was narrower, if these were very similar in electrophilicity, we may not see these results, right? In the next video for the unit, we'll start looking at, well, how could we change the structure of sodium borohydride so that we actually could reduce things like